Hi, my name is Alvin. So today I will be presenting the introduction for the PCE part. So first of all, this section introduces the reaction unit in the production of cumin. The main equipment involved are the cumin distillation column and the alkylation reactor. Next, these are some basic equations used in this study, including mass balance, energy balance, heat of formation, and heat of combustion. So this slide shows the main unit operation in this process, including the pump, heat exchanger, reactor, mixer, and distillation column, each playing a role in transporting, heating, reacting, mixing, and separating the chemicals. Next, we apply mass balance. So before start the calculation, we need to do some assumption. So we assume that the feed flow rate is 55.25 kmol per hour, containing 81.45% cumin and 15.55 DIPB. Next is the DOF. So the final answer of DOF is 0, means this system is solvable. Next is the molar flow rate. Using the mass balance, we determine the molar flow rate of each stream, where the total input and total output remain 55.25 kmol per hour. So next, the mole fraction represents the composition of each component. The feed contains about 0.81 cumin and 0.19 DIPB, while the products are separated into different streams. Finally, the mass flow is calculated by using molar flow rate multiplied by molecular weight, and the result confirms that the overall mass balance is satisfied. That's all for my present. I will pass it to Zara.
Moving on, I will now talk about the reactive system as well as the energy balance for both reactive and non-reactive systems. For the reactive system, we have chosen the alkylation reactor as our component. We assume the reactor to operate at steady-state operation, where the feed stream to the reactor is 250 kmols per hour of benzene and 50 kmols per hour of propylene, where the propylene conversion is 90% in the reactor. Only 3 components are considered in the reactor, mainly benzene, propylene, and cumin. For the molar flow rate, we used the equation of C6H6 plus C3H6 producing C9H12, all in the stoichiometry of 1. For propylene, the output is 5 kmols per hour, benzene 205 kmols per hour, and cumin 45 kmols per hour. For the molar fraction, propylene output is 0.02, benzene 0.804, and cumin 0.176. For the mass flow rate, propylene output is 210 kg per hour, benzene 15,990 kg per hour, and cumin 5,400 kg per hour. For the mass fraction, propylene output is 0.01, benzene 0.74, and cumin 0.25. Moving on to the energy balance, for a non-reactive system, the reference point of C9H12 and C12H18 is at liquid state, 25 degrees Celsius and at 1 atm. S8 will be at 120 degrees at 1 atm, S11 152 degrees at 1 atm, S10 200 degrees Celsius at 1 atm. For the energy balance, we use data from the table B2, so our total Q is equals to 2,912.67 kilojoules per hour. For the energy balance of reactive system, the reactor is assumed to operate isothermally at 250 degrees Celsius, and the reference state for all components is at liquid state, 25 degrees Celsius at 1 atm. For the energy balance of reactive system, we used an extra information of extent of reaction and heat of formation. So the total Q gotten from this energy balance of reactive system is negative 5,199.84 kilojoules per hour.
Alright, thank you Zara. My name is Adam and I will present the fluid mechanics aspect of our cumin production plant design. The fluid mechanics is critical because it allows us to determine the technical feasibility of the plant. By analyzing the characteristics of our piping systems, we can ensure the optimized delivery of our products from the initial feed mixing all the way to final storage. Moving on to our piping layouts, we have designed 11 primary pipelines labeled P1 through P11. Summary: All pipes are constructed from stainless steel 316 for its high strength and superior corrosion resistance, and we also utilize three different nominal diameters: 1.5 inch, 2 inch, and 3 inch Schedule 40 pipes, chosen based on the volumetric flow rates of each stream. Regarding components, we have mainly integrated gate valves for unobstructed flow and long radius elbows to minimize resistance, among other components. And regarding spacing, our pipe length ranges from 5 to 12 meters to provide adequate clearance between major process units. Now, this table provides a comprehensive summary of our fluid properties and calculated pressure drops. Regarding flow regimes, based on our Reynolds number, all our streams operate under turbulent flow. You will also notice significant pressure in P1 and P2 due to the work added by our feed pumps. And regarding system losses, in the remaining lines we see energy dissipation quantified by the friction factor and head loss. For example, P9 shows a higher pressure drop of 3758 Pascal because it utilizes a globe valve for precise flow regulation. To ensure our calculations were both realistic and accurate, we made several key engineering assumptions. For example, we treated all liquids as incompressible and our pumps operate at 85% efficiency. Besides that, we assumed negligible changes in elevation and velocity within each pipe section. And finally, our densities are calculated based on the specific material composition in each pipe. For example, 862 kg per meter cube for pure cumin to provide the most accurate pressure drop modeling possible. Now I'll pass to Alicia.
First, I calculated the flow conditions for P1, which is the benzene stream from pump 1 to the mixer. The molar flow rate of benzene is 60 kmol per hour. Using the molecular weight of 78.11 kg per kmol, the mass flow rate becomes 1.302 kg per second. Using the density of 876 kg per cubic meter, the volumetric flow rate is 0.001486 cubic meters per second. With a pipe diameter of 0.0525 meters, the velocity is 0.686 meter per second and the Reynolds number is about 70,000, which indicates turbulent flow. Next are the calculations for P11, which transports cumin from the column to storage. The production rate is 10.25 kmol per hour, which gives a mass flow rate of about 0.342 kg per second. Using the density of 862 kg per cubic meter, the volumetric flow rate is 3.97 times 10 to the minus 4 cubic meters per second. With a pipe diameter of 0.0779 meters, the velocity is around 0.083 meters per second and the Reynolds number is about 25,000, which again shows turbulent flow. Next, this is our strategy for delivering the main product. It will explain how the main product cumin is transferred and also stored. Cumin is produced from the alkylation of benzene with propylene and leaves the process as the overhead stream from the cumin column. The vapor is first cooled in a condenser, turning it into liquid and then collected in a reflex drum. From there, a centrifugal pump transfers the liquid cumin to the storage tank. For equipment design, we selected a centrifugal pump with 75% efficiency, which is suitable for continuous hydrocarbon flow. Although the calculated power is small, we selected a 0.5 kilowatt pump to ensure reliable operation. The storage tank is a vertical cylindrical tank made of carbon steel ASTM A36 with a diameter of 6.5 meters, a height of 10 meters, and a capacity of about 335 cubic meters. Simplify the design calculations, several assumptions were made. The flow is assumed to be steady, fully developed, and incompressible. The pipe length is 30 meters and the elevation difference between the column and storage tank is 8 meters. Pump efficiency is 75% and minor losses from fittings and valves are also included in the system calculation. Using the system data, we calculated the friction loss and pump power requirement. The Reynolds number is about 25,400, confirming turbulent flow, and the friction factor is approximately 0.0061. The total head required is about 8 meters, including elevation and friction losses. Based on this, the pump power required is approximately 0.036 kilowatts, so a 0.5 kilowatt pump was selected for safety. In conclusion, this project demonstrates how fluid mechanics and chemical engineering principles are used to design a cumin production system. By calculating flow rates, pressure losses, and pump requirements, we ensure that the pipeline system can transport cumin safely and efficiently. Proper equipment selection, material choice, and safety systems help ensure reliable plant operation.